So,
Sorry, we just realized we need to record.
okay. All right. I still get paid, right?
We actually double the amount you get.
Okay, excellent, double. So here's Carl Jansky, 1932. He was making it work. He's kind of the father of radio astronomy, I guess. Then, 1937, this fellow, Grote Reber, just a few miles where I was born and raised in a suburb of Chicago called Wheaton, Illinois. He set up this dish 9 meters across, made out of sheet metal, with a receiver, and he started getting data. It was a successful dish, and I can only imagine what my HOA would say if I had put up that in my backyard. I'd be going to meetings with them. By the way, the picture in the center, the color picture, is that antenna has since been, in the 1960s, moved to a big radio observatory in West Virginia called Green Bank. They have a very big radio telescope there. And so have a road trip, you can go see Mr. Reber's antenna. So that's the first parabolic radio antenna. And of course, you may know, we used to have a 1,000-meter radio antenna in Arecibo, Puerto Rico. It collapsed, it fell apart in 2020. So it was out there for a long time, almost 60 years. And it was terrific, but no more. But there are several others now to take its place, that's for sure. So then this fellow, Martin Ryle, he came up with an idea. He invented something. I don't know how else to put it. He figured it out. The idea of aperture synthesis, and aperture synthesis goes kind of like this, as they say in the song. If you've got a 10-meter radio telescope and a second 10-meter radio telescope, and let's say they're 100 feet apart, and if you combine their signals just right, and I'll try to tell you how that's done, then you don't get the resolution of your image like 20 meters, 10 meters plus 10 meters. You get the resolution of a dish that's 100 meters apart, because the two dishes are 100 meters apart if you combine the signals just right. And of course, you might be figuring out, if you don't know already, that's the idea behind the VLA, but we'll get into that more. So as you can see in the picture, he got a Nobel Prize at 30 years later, something like that, for doing this, because doggone it, you can get tremendous resolution with aperture synthesis at radio telescopes. So aperture synthesis, here's a description. It's a type of interferometry. If you don't know what that is, I'm going to be explaining it to you as good as I can later. That mixes the signals from a collection of telescopes. You can have 2 or 50 or whatever, to produce images that have the same angular resolution as an instrument the size of the entire collection, which is what I just kind of tried to explain. If your radio telescopes are 100 feet apart, you get the resolution of a radio telescope that's has a dish that's 100 feet in diameter. So that's aperture synthesis. He's the fellow who figured that out, and that was huge for radio astronomy, to be sure. Now, how does this work? First of all, each of your antennas, whether you have 2 or at the VLA, there's 27, the location has to be very precisely known. I think maybe down to the centimeter, okay? Then they have to be pointed at the same object at the same time. Item number 3 says, okay, so these are radio waves coming from a black hole, let's say, and they have peaks and valleys, these waves. Now, we're talking about things moving at the speed of light, and these peaks and valleys are very, very small, but there's still peaks or valleys that are in the waves, and they refer to that as well, anyway. And when these peaks arrive at each antenna, has to be measured with an atomic clock, all right, to get interferometry to work, all right? And when if the 2 antennas are at 2 different locations, the peaks are not going to arrive at them at the exact same time as measured by the atomic clocks. So you got a wave coming in at the same time as a valley. That's called interference, when the phases are not lined up and in phase with when the peaks are not in phase with each other. That's the interference part of interferometry. So you come up with these fancy computers and electronics, so we're going to talk about them more, and they measure the difference, and then they get them in phase. The computer is called a correlator because it gets the peaks and valleys in phase, and that's key to getting the resolution of the dish, the size of the distance between your dishes. Okay, so measuring this interference, as it states there in item number 7, that's interferometry. And the VLA has 27 telescopes, and the distance between any two telescopes is referred to as a baseline. You can do the green math there in your free time. All right. And that says that for when you got 27 of them, you get 351 baselines at the VLA. So you got to have a pretty fast, fancy computer / correlator to get all these peaks and valleys in phase with each other. Okay. And of course, the Earth's rotation doesn't help you any. You've got to take that into consideration because all these antennas are moving. And that's item number 9. Now, item number 10 is the mathematics that's used inside the correlator computer and to get these peaks in phase with each other. Now, if you want to know how this equation works, you're going to have to talk to somebody else. Okay. I spoke with a couple of different people who are math, they walk on water with math. Okay. And they said, no, Bill, I can explain this to you. And I kind of got it, but I really didn't. All right. And these two guys, they're really smart. One man, one lady. And I don't have it. So, take a screenshot and then you work on that on your own free time. But that's the equation. It's called the Fourier transform. And that's what you need to make interferometry work. So what does it say? Item number 11, as the antenna moves to follow the object, additional perspectives are obtained. That's kind of like what I said before about the fact that the Earth's rotating. And so item number 12, I'm sorry, this is a long list here. The baseline, the separation between any two telescopes, determines your resolution. If the baseline is longer, the telescopes are farther from each other, you get more detail. If they're more closer together, you can see dim objects better, low surface brightness objects better. And because you get those two different situations with longer and shorter baselines, that's why the 27 radio telescopes at the VLA are movable. And we're going to get into that a lot more. I'm going to take a breath now. Okay. So yeah, aperture synthesis, it's very difficult for me. This is an actual Tylenol ad, and it definitely gives me a headache. So the fellow who invented interferometry, here's the telescopes he used in England in the 1940s in Cambridge. And as you can see, they're several yards away from each other. And so he had to use interferometry to get the high resolution. Of course, these telescopes were not movable. So here is the timeline of the construction of the VLA. Matt, my brother, who was older than me, we heard about it in the 60s that they were trying to make this happen. And we just thought, man, if there's anything the United States should be spending its money on, it's facilities like this. We couldn't wait for this to happen. In 72, it's approved. 73, they start construction. 75, the first antennas there. 76, they get what they call the first fringes. They were getting the first radio signals in their antennas. The whole thing is working in 1980, 1 year early. $78 million in 1972 within budget, which is about $1 per taxpayer. And we thought this was a great thing to spend money on. So then, this is my daughter and her husband and my grandson, who was just about 2 years old back then. In 2010, they went on a trip and went to the Grand Canyon and a meteor crater and the Lowell Observatory and the VLA and some other stuff. Yeah, I've infected my daughter with interest in astronomy. So they went on this trip and saw all those nice places. And then they were living in El Paso at the time. Then I was at their house at El Paso, and my son-in-law Jack says, Bill, come on, let's go to the VLA. I'll take you. And I said, well, when? He says, let's go tomorrow morning. Like nothing for him. And I said, that's a long drive. Yeah, no problem. We'll get there in no time. So here's the route from El Paso to the VLA. It's sort of in western New Mexico, and it's all this desert highway. And I saw my first Roadrunner. It was just an amazing trip. And we were moving along really well. He's got an extremely fast car. And at one point, I looked at the speedometer. We're doing 90. Okay, so we got there really quick. You might not get there that quick, but so we're driving down the road, and then all of a sudden, I look up and I see an antenna. Oh, wait a minute! No, that wasn't the VLA yet. My mistake. I thought it was an antenna. It wasn't. We went a little bit further. I'm looking for a long string of white antennas. Right. This is what I'm looking for, and then I saw it. Oh, wait a minute. No, that wasn't the VLA either. Okay. They're white, they're tall, there's a bunch of them, but no. And then Jack said, Bill, you see that rise in the rows ahead of us? When we go over that rise, we're going to be there. We go over the rise in the road, and this is what I see. Well, let me tell you something. Right now, I'm getting a little emotional looking at this because I was waiting to see this since the 1960s. Okay. And I see this, I said, whoa, Jack, pull over. I got to get the picture of this. You got the desert landscape, the blue sky, the white antennas. I just went nuts. I love that picture. And as you can see, they're all pointing in the same direction. That's what they do over there, right? And then we drove just a short while longer, and you see the railroad tracks. Doggone it, I know what those are. That's how they move the telescopes around. Okay, so I took a picture of that. And there's a sign saying to get in, you go this way. You get to the front gate, you see a really nice sign here. And but this was my favorite sign. This was made by some person who knows how to do plasma welding to cut these shapes in thick pieces of steel. And it's very simple, not fancy like this, colors and everything, but I just love this sign. Anyway, of course, when you get inside, you see the new name, Carl G. Jansky, very large array, and you see the antenna over there. There is no guided tour there. It's all a self-guided walking tour, which was great for us because, you know, we didn't pay attention to any signs. Anyway, so there is kind of the entrance. So here's yours truly. You're going to find out, well, you may already know, sometimes the antennas are close to each other, sometimes they're far away. On the day we were there, they all were close together, so you get these great pictures. You see all 27 antennas in one shot, right? And on the left, you can see they had several rules. One, they don't like gas-powered cars. It's not because of the gas, it's because regular gas engines use something called a spark plug, which, and by its name, is constantly sparking, puts out electromagnetic radiation, the whole ignition system, and that does not help them. Oh, by the way, just about every time you see pictures of these antennas, there'll be mountains in the background. That's because this location is in a ring of mountains in a big bowl, and obviously to keep out stray electromagnetic radiation. So they like diesel engines in here. We didn't have one, but they didn't stop us. So, but that's what they say. Also, cell phones got to be either off or in airplane mode. They don't like Bluetooth or Wi-Fi or drones, and just to keep out the interference. Okay. And then there's these signs here that tell you don't go any further. Again, that's just a suggestion. I went a lot further and got some nice pictures. I got a good attorney, so I wasn't worried. Anyway, and to me, it's an absolutely beautiful site. I knew the chances of me getting back there were slim, so I had to get some good shots there. Now, I did not take this picture, but this is the VLA from orbit. Okay, and you see this. Oh, by the way, can you see my cursor moving?
Yeah.
You can. Okay, good. So here's the railroad tracks. Okay, we saw them from this road over here, and the railroad tracks are in a Y. All right, and if you look closely, you see all these little dots. Those are the actual antennas. Here's the actually, this is a maintenance facility and the visitors center and stuff like that. Anyway, so that's how the railroad tracks are laid out, and you can see it from orbit. And you may know that I just told you a minute ago that it came online in 1980. Well, in the same year, Carl Sagan, bless his heart, I miss that guy, He did the Cosmos series, came out in 1980 on PBS, and he filmed the several segments at the VLA. I don't even know if it was working at the time, but I assumed it was then. But anyway, so that's one time when we got to see it before I went out there. And you may be familiar with the movie Contact, which many scenes were out at the VLA. This is Jodie Foster, who in the movie was looking for, was doing SETI work, a search for extraterrestrial intelligence. And by the way, if you haven't seen the movie, I strongly recommend it. It's dynamite, in my opinion. And 1996. And so she was using, supposedly in the movie, all those antennas to do her SETI work. But if you would have asked the VLA people, they go, no. We don't do SETI here. We just do real professional, conventional radio astronomy here. They did it in the movie, but we don't do that. I'll talk more about that later. They have a display over there at the visitor center that shows the filming of the movie. Okay, so here is the picture from orbit again with that the Y shape of the railroad tracks, the brown lines over here. Okay, so it's centered over here, and the antennas can be moved along these tracks in 4 different configurations. On the left, you can see the distance between of the diameter of each of the configurations in miles. So the day we were there, they were in configuration D, where all of the antennas were within half of a mile, more or less, of each other. Okay, and you can see when they're in that, they're looking for dimmer objects, and they can only resolve 200 to 1.5 arcseconds. And then in configuration A, you can see the diameter configuration here in the upper right-hand corner. They're 22 miles in diameter. All right, takes them a while to move all those antennas that far, but they're much higher resolution, between 6 and 0.05 arcseconds, and configuration B and C in between those numbers, right? So again, as I mentioned before, with aperture synthesis, when you're this far apart, like in configuration A, you can get these high resolutions because you're simulating a dish that's 22 miles in diameter. So doggone it, imagine, if you got a reflector, you can get a mirror that size that works. So those are the 4 configurations. It takes them a couple weeks to make those moves. And that's about that. Okay. So the different configurations give you the different resolutions, but also, as you can see in this chart, here's the 4 different configurations, and here they are laid out. And here are the different frequencies that they can all look at, because each dish has many receivers for different frequencies. And here's the resolution in arcseconds. So here's A, where they're far away, highest resolution, 0.05 arcseconds, as we saw. When you're in frequency Q, whatever that is, and then you've got all these different frequencies, and so configuration A will give you different resolutions depending on the frequency, and the same is true for the other configurations also. So it's the configuration that you're in plus the wavelength that you're looking at, the frequency that you're looking at, same thing, that determines the resolution. So here they're looking at one object. It's a very active galaxy. And in configuration A, you get this, in B, you get that, in C, you get this, and D, you get that. You might look at D and say, why bother to do that, right? A might look like the nicest one for you. But the key is you put them all together. In other words, you take observations in configuration A, then you take 2 weeks, move them to B, look at the same object, move them to C, the same object, you go to D, same object, and then you can put them all together with your correlator, and you get an image like this. And, I think the bottom line is that system works well. All right. Okay. So I've been talking to these people. As you might have seen, I went there in 2010. So I've been keeping in touch with them. And I was there talking to them just the other day. And I said, hey, tell me the list of the most significant results that you can offhand that you could tell me from the VLA. And they listed these 5 here. Water ice on Mercury in 91. They're not in chronological order. 2017, the first detection of a radio from a gamma ray burst. 1987, the first radio images from an Einstein ring, if you know what that is, when you're using a gravity lens, you can see a ring of an object that's way behind a very massive object. We've seen them with the telescope, with the regular visible light telescopes, but they were the first ones to get radio images from one. 1999, they were first detected a microquasar in the Milky Way. 2011, they discovered a supermassive black hole in a dwarf galaxy, which was the first. So they've made a lot of discoveries with the VLA. So here is yours truly and my my son-in-law, Jack, the fast driver. And here's an antenna we were able to get real close up with. I'm pretty sure they have, when you're in the deconfiguration, this antenna is one that you can always get close up to. And, you know, and my son-in-law Jack took this nice picture. You see the whole antenna there. We had a beautiful day, a nice blue sky. And here's a little close-up view. And here's stairways for maintenance people. And this is a gear, a tooth to gear, if you will, a segment gear of a gear to change the altitude of the antenna. And by the way, when you're this close to the antenna, I could hear the electronics humming in this thing, even though it's probably 50 feet up, but I could hear the electronics in it. That's how close you're able to get. So that's the altitude gear. All right. So yeah, I took a lot of pictures of it. And then we walked around and we saw the signs that said, don't go here. We went there anyway. And we took nice pictures. And so, as I mentioned, there's not just one band on each antenna. They have 10 receivers on each antenna. All these megahertz and gigahertz. Maybe you will know what some of this stuff means. I have to admit, I do not. But the point is that they didn't always have 10 receivers. These antennas have been upgraded, and they maintain them religiously, and they're constantly being upgraded. So you can see here, there's a dish. I did not take this picture. I mean, we ignored some signs, but I didn't climb into the dish. Anyway, I didn't even think about that. That would surely be funny. Anyway, you can see the receivers there. So let me see. So there's the receivers. There's a whole bunch of them. And so the radio waves hit the dish, the parabolic dish. They get reflected to this, which is nothing more than another dish that just reflects them down to the receivers. Okay. So what? So it says here on the right, some of them are super cooled. They have very updated receivers to get increased sensitivity. The original design with the receivers back in 1980, they could get maybe 2 or 3 images a day. Today, if they have a strong isolated source, they can do an image in a couple of minutes. And so they've been upgraded over the decades. So that's really great. So here's a close-up of the receivers. They're a lot bigger when you get close up and you see how big they are next to a person. And, you know, I can see like 4 or 5 of them here. Again, there's 10 of them on each antenna, and these are maintenance guys. And I got a little video later that shows you them. I hope we have time. That shows you doing maintenance on some of this stuff. Here in the visitor center, they have a cutaway view of what a receiver looks like. I think it's an old one. And then what used to happen in the original wave guides, it says, so the antenna feed would come in, and they didn't convert it to electricity or digital back in 1980. They would actually send the radio waves through these tubes, waveguides. The actual radio waves would move through the tubes. This is a rotary joint because the antenna's got to be able to move, right? And the waves would actually propagate through these tubes and eventually get to the correlator when they're converted to some sort of analog signal. But they don't do that anymore because it's all been replaced by fiber optics, which, as you can imagine, is a lot more efficient. Gives them a higher quality also. So again, I did not take this picture. However, you see the railroad tracks, okay? And here's again, the antennas are close to each other. And then you see these railroad tracks at a right angle. Well, none of us have ever seen a train make a turn on a right angle. That doesn't happen, okay? Not that I know of anyway. So they go along the railroad tracks. I'll show you how that works later. And then somehow they have to make this right angle move and get over here. I'll show you how that works. And that's how they move these antennas around. And this is how they do it. They have these things called transporters. Why is it called the Jack of Diamonds? I do not know. But my son-in-law Jack liked that idea. So it operates with diesel engines, of course. And it's, as you can see, the big wheels for the railroad tracks. And it's got this big flatbed over here. It's a big, powerful device. Now, when we were there, this particular antenna was in a hangar getting maintenance done on it. And as you can see, the red transporter, what it does is it slides that flatbed underneath the antenna. Here, the antenna is sitting on these concrete piers. It's exactly how they're going to sit when they're out in the field, ready to do work. And so these piers are at the same height as out in the configuration. And so the red machine slides the flatbed underneath it, and then the flatbed just picks it up and takes it for a ride. Here's a picture. It takes 2 weeks, as it says there, to change the configuration, and they obviously don't move very fast. But this is how they do it. And this is all designed in the 1960s. So I think it's brilliant. Here you see the transporter with the antenna on it, maintenance personnel, and you can see the railroad tracks that it's on, and then you can see the small railroad tracks that are at right angles to the main tracks. And so the secret of how they do that isn't shown here, but you'll see it later if I get to show my videos. We'll see if we got time. So, and then here's a close-up. You can see the maintenance guys. They actually bolt these things down. And of course, they must be on these concrete piers because, as I said earlier, they have to know for interferometry the precise location of each one of these antennas to make it work. So they can't just on a higgledy-piggledy move them anywhere they want. They have to be on these piers. Okay. And then at the visitor center, there's a sculpture there that is in the Y shape to, be like the Y configurations. So there was a sign that said, do not go past this sign, which we quickly jumped over. And we looked through the window and you can see the computers, which they don't call them computers, they call them a correlator. And of course, the correlators were built in 1980. They came online, but they've been significantly upgraded. The new correlator, these are made in Canada, by the way, and is called a WIDAR, wideband interferometric digital architecture. Easy for you to say, perhaps. This new architecture came online in 2012. Before that, they could have 512 channels per baseline. Now it went from 512 to 16,000 channels. And, in the mid-1980s, I worked with IBM the large IBM mainframe computers. And the big one we had could process 1 million instructions per second. We call that a MIP, 1 million instructions per second. And we thought that was fast. We had 2 of them. So that's 2 million per second. And, 2 million of anything per second, I think is pretty fast. But these new correlators, they got to get these waves coming in at the speed of light and get them in sync. These things can do 10 to the 16th operations per second. They don't even have a word for that. Okay. I don't know I think it's between a septillion and a quadrillion or something, whatever, it doesn't matter. Super fast machine. It can input 2.5 terabytes per second. Right? They have to, again, to do the work that they have to do. And you may know that mainframe computers have to be in air-conditioned rooms because they generally put out heat. Hey, your laptop, desktop PC at home gets hot. Even your phone gets hot because electronics put out heat. Well, when they move from one configuration to another, some of the configurations make the computers actually get hotter. They're processing so many instructions per second when the configuration changes. Anyway, so that's what they look like. You know, they're black boxes. Here's your typical black box. So at one point, we were walking around and we saw these antennas that looked very different. And I asked somebody, and they explained that those two antennas in the foreground were so-called advanced technology antennas that they were testing there because the VLA's got all the facility to do that kind of a test, the correlator, et cetera. And that was in 2010. And if you look closely at them, you will say that, boy, these are the kind of antennas that people are using in their advanced technology radio observatories around the world. Matter of fact, both of these designs, well, I don't know what those two designs mean, were being tested over there at the time. So this is the new technology. And VLA, the Jansky VLA on the left there is uses aperture synthesis. It's not the only radio observatory that uses aperture synthesis. Obviously, you have to have multiple antennas. So up here on the upper right in Hawaii, on top of Mauna Kea, I got to visit that place once. All of these small antennas you see down here are in one big synthesized aperture radio observatory. In Chile, you have ALMA. In Australia, you have ATCA. I'm sure that those things mean something. In France, you have IRAM. In California, you have CARMA. These are all radio astronomy observatories that use aperture synthesis. I did not take this picture. Okay. I wanted to show you. I did not take this picture. This is in the deconfiguration as it was when we visited there, but I did take these pictures. I happened to be flying the 1990s, I think it was, from San Diego to Chicago. And I look out the window and I went, holy mackerel, I know what that is. And I hadn't visited it yet. So I got out my, who knows what kind of camera I had. I don't even remember. It wasn't a phone. It was a real thing we used to call a camera. And took these pictures. And they're lousy pictures as pictures go, but I was happy that I was able to see it at altitude. So again, I really liked them, so I took lots of pictures. I just love the view. So I also asked them, hey, I was talking, this is just last week, what's the projects that are going on right now? And they basically said, can't tell you, because each one of these projects is associated with an individual scientist. And, you know, they don't like to give out their information until it's ready for publication and it's released to the public. So they really couldn't tell me of anything of significance that they were going on at the VLA. However, they were able to say that since 2017, they've been actually doing a radio survey of the whole sky that they can see from their location, the Very Large Array Sky Survey. It's going to be at 2.5 arcsecond levels. So I don't know what percentage of this project is completed, but that's something that they're involved in right now. And but they generally, on the bottom there, they generally use to study masers, black holes, protoplanetary disks around young stars, and the physical mechanisms that cause radio emissions. For instance, like why do black holes and quasars put out a bunch of radio waves, that kind of stuff. And then, if you recall, in 1996, when they made the movie Contact, they said, oh, no, we don't do any SETI. Well, just a few days ago, May 1, all right, 11 days ago, they announced this new project called Cosmic, where they're looking for techno-signatures. Now, one of the big problem with doing SETI work was that, well, if you're doing SETI work, you take telescope time away from doing conventional radio astronomy. And the radio astronomers don't want to do that. They kind of considered SETI, you know, a second-class citizen, sort of. They wanted the telescope time for their work, and everybody sort of stuck with that. But they figured out a way that they could just piggyback the actual regular conventional astronomy runs and get data for SETI. They're going to be looking at 10 million star systems. As it said, they tested out the system. They were able to detect the Voyager spacecraft signals, which are weak as heck, right? 15 billion miles away. So the system generally works. And again, they just announced it a few days ago. What's going to come of this? I do not know. If you hear of anything, let me know. We'll see what happens. I never thought I'd hear this, but as a matter of fact, in the movie Contact, they were talking about the concept of how SETI was the second class project, and the VLA people didn't want to do it. The government people, the funding people didn't want to do it. But here we go. So that's that. Then if you go there, there is Astronomy Club there. Enchanted Sky Star Party. Magdalena, New Mexico is very close to VLA, and it's done in association with the Night Sky Network, Astronomical Society of Pacific, and the JPL. You see the view in the lower right over there. They got dark skies over there, that's for sure. They did something for the meteor shower over there on the 6th and the 7th. Anyway, so if you're going there, contact Enchanted Skies, and maybe you can do something with them too if you want to do some viewing. I'm sure it's dark skies. Okay, so I've got 2 videos to show you. Do we still have time? I got one video that's about 7 minutes and another one that's a series of very short ones about 5 minutes. Do we still have time for that, Joyce?
Yes.
Okay. All right. I have to, let's see, I have to stop share and then go back to share again. And here is my 7-minute video. I know you're going to think this was a Scorsese movie, but it isn't. It's just what I did. And so here's my video. It's about 5 minutes. Excuse me, 7 minutes. And it doesn't seem to be working. Shoot, I tested this and everything. All right, let me try this again. Share. Oh, I was pointed at the wrong one. I have to point at this one. Give me a chance. I'll screw up a Zoom. Now, do you see the little screen?
Yes.
Yeah.
You do. Okay, so this should work. There's sound on here, I hope. Did you hear the sound there?
Didn't hear the sound, but we saw the video moving.
Shoot. I thought I had this. You know what? I don't think the sound's important. I'll narrate. Okay.
Okay, that's fine.
So you can see the mountains all the way around the whole facility. Keep out the interference. Approaching VLA.
We can just barely hear the sound.
Oh, that's because it's coming over my microphone.
Oh, okay. Yeah.
Wait a minute. Is that louder?
No, it went away completely.
Okay. I'm gonna shut off the volume. Okay. All right. So here we are close to an antenna. Just doing our walking tour. And we can get up nice and close to this one. Close to it now. And from this distance where we are when I took this video, I could hear the electronics already. You can see this. Look at that. Look at that. So I don't think you're going to be able to see this here, but wouldn't you know it? They were doing this to mess with me. They'd start to move all the antennas together. I'd reach for my video camera. I turn it on. There's a little bit of delay in the video camera. And right about the time I start taking movies, they stop moving them. They did that 3 times. I think they were looking out the window and they saw me doing it and they said, well, let's mess with this guy. So I don't think you can see the antennas moving here. Anyway, they were just messing with me. And of course, when they move, they all move together. And when that big thing started to move, it really got my attention.
Objects. There's the antenna that we were at. Watching.
So that's the one we got up close to.
It's the family. Laid out the so-called configuration. And they're busy today. We know they're working because we saw them moving.
Yeah, I took a lot of pictures of the antennas. Okay, so.
Assembly building. Here, Bill, what you got there? The background.
So that my son-in-law's taking the picture, that's me. And so there's an antenna that's in that hangar to do maintenance, and you can see the red transporter underneath it. Yeah, they have spare antennas so that if they have to take one out for maintenance, they can still have the full complement of 27. I can't apologize for these videos. That's my son-in-law. You can see the mountains are 100% all the way around this facility.
You can see I'm standing right under a dish, right next to the antenna assembly building, and the dish is on the solid foundation.
So you can see the way the 3 piers work that are perpendicular to the regular tracks. I'll show you later how they do that.
Take you right out to the rest of the dishes are. So obviously they all roll along these railroad tracks, but when they get to wherever they're going, they get off of their wheels and they get lifted and placed on these solid tripods of concrete so that the into the dish.
Okay, so now I'm just saying it's a great place. You got to come and visit sometime. Okay, that's that video. Okay, sorry about the sound situation. Screen sharing has stopped. Oh, yeah, that's because I clicked out of it. Okay, so now I'm going to show you the last video. This is about 5 minutes. And that is where, that's this guy here. Okay, I do believe. Yeah, this is about 5 minutes. We're going to see a bit of a video about the doing maintenance up on the dish, on the receivers, a little bit of video about the transporters and about the correlator.
Miles away
Do you see the video moving?
Yes.
Okay.
from the safety of the lab.
Oh,
Another
wait a
crew
minute,
is
though. You're not
dispatched
going to
to
hear the
undertake a
sound.
daunting task.
All right. So these are the guys. This is how they get inside the dish. and do maintenance
30
on the
feet above
receivers.
Each antenna's dish,
We can hear the sound.
apex.
Oh,
Every few months, personnel climb the thin beams
It's just low.
apex for critical installation and maintenance of the VLA's P-band receivers. With gusting winds, difficult footing, harnesses are a must. Only the smallest crew members can squeeze into the apex itself.
this is at the apex where the secondary
As the
reflector
crew
is up at
works,
the top
the
over here.
rest of the array is still making observations.
Code for the RCP LCP.
These low-band receivers are especially important for detecting invisible hydrogen gas in the early universe, the main ingredient of future stars and galaxies. Regular upgrades like this are crucial to keep the telescope functioning at the level required by astronomers. But the entire array has also recently undergone a complete reinvention on a massive scale. After decades of stunning science, the 1980 vintage VLA was in danger of becoming obsolete. Without the resources to construct a new instrument from scratch, NRAO devised a strategy to rebuild the telescope from the inside out.
We were able to conceive of a plan that would keep all the antennas the same, keep the rail tracks, keep the infrastructure that supports this instrument, but completely rebuild the electronics.
Over the course of a decade, crews have worked to replace nearly all of the technology inside the telescope, creating a new instrument within its original skeleton. At the center of the VLA expansion project is the development of a new supercomputer called the Correlator. In a meticulously controlled clean room environment, this incredible machine, contributed by Canada, turns 27 radio dishes into one gigantic telescope. Huge data streams from each antenna are fed to the telescope's control building, where the correlator increases the telescope's capabilities more than 2,000-fold. After a 10-year effort, the reinvention of the VLA is finally complete. To integrate the newly upgraded antenna with the rest of the array, the telescope's maintenance
Here's
crew
how
must
they,
perform another vital task high on the desert
Here's
plain,
how they move the
in an
telescopes with the
intricate dance
transporters.
between man and machine. Not only do the VLA's antennas move to track objects in the sky, they also move throughout the array itself, on the backs of custom-built antenna transporters. Engineers maneuver these 90-ton flatbed locomotives underneath the antenna's triangular base. 230 tons of steel and sensitive electronics is hoisted into the air, and the 94-foot-tall structure is slowly unveiled. The antenna's sheer size makes transporting it a potential hazard. The crew cannot move antennas at winds of more than 20 miles per hour. And maximum speed is just under 5 miles an hour. The array is crisscrossed by more than 40 miles of railway lines. The antennas are moved along tracks that lead 13 miles out from the center of the array to 72 separate antenna stations. These stations are connected to the main track by perpendicular spurs. When the transporter reaches the desired station, engineers use hydraulic jacks to pick up its wheel trucks independently. And rotate them 90 degrees to make the turn.
So that's how they make the turn.
They carefully set the structure down. And the upgraded antenna makes its new home in the vast array.
Okay, that's it for my videos. Let's see. I've stopped my sharing. I'm available for questions. Thank you very much for the invitation. Thank you very much for your attention. And I'm available for questions if there are any.
I noticed they were using walkie-talkies while they're doing maintenance.
What about walkie-talkies? Say again?
Well, they were working on the antenna, saying that the rest of the array was in use. They were using walkie-talkies. Communicate.
So you're saying that could be radio interference, correct?
That's what it seems like. It became a stuff. Maybe
I think you're absolutely right, except while they're moving antennas, the system's not working. So they're really not worried about interference. Okay. I mean, it's a very capable system, but they can't do it while they're on the road. They got to wait until, remember, one of the rules is you have to know where the antenna is very precisely for the system to work. And so after they move all the antennas to the configuration they want, then the no radio interference rule goes into effect.
I was talking about the part of the video where the guys were climbing up the antenna down at speed, and they were saying in the audio of that they could do that while the rest of the array was in use. I could see them.
Okay, that was, yeah, where there was just one antenna being moved to the hangar for maintenance, not when they're doing a configuration change. But if they are moving one antenna into the hangar for maintenance, that's a good point. Maybe they have walkie-talkies on a special frequency, or maybe they have to only do it when it's not being used. I really don't know the answer to that, but that's very observant of you. I applaud you on your seeing that.
Do you know if they can do longer baselines by connecting with other radio arrays around the world?
Well, such a thing does exist, but the VLA does not participate. And I asked, it's called the very long baseline interferometer or very long baseline array. These are, there's 10 radio telescopes around the world. They're all exactly the same. I think they're 10 meters in diameter. I could be wrong on that. I think that's the size of them. And I asked, why doesn't the VLA go into it? And he said the VLA, the wavelengths and the frequencies, etc., that the VLA works with is different than what the VLBA works with. And so they don't work with it. I mean, they already have 27 antennas, but the VLBA has 10 and around the world, but they do not participate in it.
And one of the VLBA ones is in near Fort Davis. I've been there.
Near Fort Davis.
Yes.
Yes.
Oh, okay. I have a diagram somewhere of where the antennas are. I forgot. Yeah, there's actually one of the antennas that participates in the VLBA is right down the street from the VLA in a town called Pie Town, P-I-E, Pie Town. And so it's right next door to the VLA, but again, the VLA doesn't participate.
Yeah, the one by Fort Davis is about halfway between the town of Fort Davis and the McDonald Observatory.
Okay. Thank you. I will apologize about the sound situation there.
Yeah, I think you're talking about the Harvard radio station, also known as the AAS station. It's just outside Prue Branch.
Oh, okay.
Yeah, go ahead.
Go ahead, Michael.
Yeah, so this, you may not be able to answer this, but for the method to work, the accuracy, you're talking about extraordinarily small differences in arrival time at each telescope because the signal is coming in at the speed of light. So I understand how the Fourier series business works, but that must be a phenomenal data acquisition. You know, they said they built this in the 80s or 50s. And when did they build E-Ray?
It came online in 1980.
Yeah, so I'm just thinking, you know, interference is one, you know, one thing, like acoustic interference, that's relatively easy to do. People do that in medicine all the time. But when you're doing electromagnetic waves at that speed, that's really phenomenal if they could do that.
I would agree completely. And we're not just talking about syncing up the radio signals. We're talking about the peaks and valleys in the radiation itself and syncing them up. It's voodoo black magic as far as I'm concerned. But you saw the equation. It's simple. They just do it that way.
But doing it.
Yeah, but your graph of frequencies versus resolution, as you go to lower frequencies, the wavelengths are longer. You have more time between peaks and valleys. And I would suspect that in the early days, they used the longer wavelengths, and what they've been doing is adding shorter wavelengths, higher frequencies for things that have more compute power, where, you know, it needs more detail, but if you got a faster computer, you can get the detail.
Perhaps so. I could believe that. I don't know that, but that sounds feasible. That sounds correct to me. Yeah.
Back when I worked at UT, we would use light delays on the order of fractions of a picosecond, and we do that by having micrometer controls on mirrors.
Okay.
You tweak a mirror by 1,000th of an inch, and you adjust the time by a fraction of a picosecond.
You showed a picture of a waveguide from the original installation, and I'm wondering, was that completely electromechanical or was there computing involved in the correlation for the original?
Oh, yeah. It was a correlator going back all the way to 1980. They had a correlator. They just upgraded it in 2012.
Okay.
Yeah, I don't think they can do this work without that advanced correlator technology.
I wondered if maybe that waveguide was measured to whatever length so that mechanically you synchronized all the wave fronts, but maybe that's not possible.
Yeah, I think those wave fronts are just too fast.
Any other questions for Bill?
Yes, I was wanting to ask about the video that you played, Bill. Well, the last one is that the one that's narrated by Jodie Foster, or I think I had seen that one a while back.
Oh, shoot. You know, it might be. It might be. I'd have to. That sounds familiar. It might be. You know, she did the movie, so.
Yeah.
Yeah.
I just happened to stumble on it on YouTube. But did you find those then from like the VLA website or something? They're pretty interesting.
I'll be honest with you, I don't remember. I think when I was there, they pointed me to it.
Oh, nice.
You know, I said, I need more info, and they said, go look here.
Very cool. Thank you.
You're welcome. Thank you.
Is it okay to ask a question?
Hey, you paid for a ticket. You get to ask. Yeah. Well, and as long as you want, I got to be home by midnight, though. I got to be in bed by midnight.
First time I've spoke up. I've joined you guys before, but in that upgrade, the video, the last video you showed, they talked about the upgrade. And other than, you know, my common thinking would be that they upgraded processors and more advanced technology. Do you know any of the specifics of what they did to make it? If I understood correctly, they said it was like 1,000 times more powerful.
Yes, yes. I don't think they really changed anything. I think the correlator is completely different. Completely different. You roll out the old one, roll in a new one. You know, it's super advanced compared to the old one. I don't think you can just, you know, change the timing and put in better spark plugs and make it faster. You have to have a whole new system.
So,
Today's
I'm sorry.
today's computers, execution speeds for fast computers are measured in teraflops.
There you go.
Which is 1 billion MIPS per second. So what's available in computers today for a really fast computer way eclipses anything that was available in the 1980s.
That's for sure.
Right.
Yeah.
But you don't know any of the other specifics other than just upgrading the technology. That's
You're correct. You're correct. I do not know that.
okay. Just
Wiring something. It seemed to me that they were upgrading the receivers at the same time, not just
Right, the correlator and the receivers. Yeah.
Yeah.
That was probably the change from the waveguide to the fiber optic.
right. Yeah.
And then there was that change too. Correct. Yes. Well, somebody was awake while I was talking. That's great, man. Thanks, guys. That's
Several
great.
of us.
I appreciate it.
I'm digging your surroundings there. I'm wondering if we could go on a field trip and come visit.
Come visit what? Oh,
You?
my
Yeah.
office?
Yeah, that's awesome.
You know, I keep too much stuff, man. I could take you on a tour, but you know, then you would all fall asleep.
It kind of looks like the lab room over there at St. Stephen's School.
Oh, really?
Where they have
Ooh. I'll tell you, here's something interesting. You see in the upper left-hand corner, those black and white images?
Yep.
There is
You're not sharing.
Pardon me?
You're not sharing anything.
Oh, you have to just look at me and then look, you have to look over here at these two black and white images. There's a planetarium in Chicago called Adler Planetarium, the first planetarium in the Western Hemisphere. It's an absolutely wonderful place. And a friend of mine was an artist there. So he was involved in many of the projects, you know, displays and art and imagery and all this stuff. And he's a special guy. And those images, they look like photographs. One of them is Venus transit and the other one is a Mercury transit of the sun, but they're not photographs. He said it was terrible to waste paper grocery bags. So on the back of the paper grocery bag where there's no printing, he did a black and white chalk drawings of the Venus transit and the Mercury transit. And you can't really tell by looking at them, but they're absolutely stunning. And so that's just one of many things that adorn my cave here.
Cool.
All right. Well, thank you so much, Bill, for your presentation.
You are welcome. Thank you. Again, thanks for the invitation. I appreciate your attention. Absolutely.
Well,
And in the
thank
future,
you also for being ready to do this, because these are presentations that Bill already has ready, and we had a last minute cancellation and we said, Bill. So, he did, and it's great. And we'll be asking you for some of your other presentations at some point in the future, I'm sure. So
you got my number. Have your people call my people.
right, we will. We will. Thank you.
You're
Thank
welcome.
you. I thought of a couple more things that I should have said earlier. One, there is a member star party a week from tomorrow. Let's hope the weather gets better by then. And the other thing was there in the newsletter today, there was a little item about McKinney Ruffs, which is between Austin and Bastrop, is looking for some astronomers to do programs there. And so I think you might be interested. Check out the newsletter. I assume it. I have looked at the newsletter. I had asked if you put it in the newsletter.
That's a paid position, by the way.
Yes, right. It's not. I don't know how much, but it is paid. All right. Anything else anybody has? Okay, well, we had said that we would go over to Easy Tiger, which is on the other, you head that way and there's Mill Pisskill Road, and it's in the Link Shopping Center that's between Mill Pisskill Road and I-35. if anybody has any other suggestions, any other places you'd rather go, we can go someplace else, but, otherwise, and we'll see some of you at EV Tiger.
All right.
All right. Thanks for coming.
Thank you.
Hey, Joyce, can you guys can you continue the Zoom from Easy Tiger?
Okay, you want to hit the end record?
What's the name of the place?
Tiger.
Easy what?
Like,
Easy Tiger.
yeah, it's at the north end of that lake shopping center.
Well, it's gonna be just.
Yeah.
So what's our next star party gonna be, you think?
With